Let us look at a question from quantum mechanics that was asked in CSIR NET December 2018 paper. It says a one-dimensional system is described by the Hamiltonian h is equal to p square by 2m plus lambda times mod of x, where lambda is some positive number. The ground state energy varies as a function of lambda as watt power. So the question asks us to evaluate the functional dependence of E with lambda. It doesn't want us to calculate the exact relationship of E with lambda, just the functional dependence. On what power of lambda does E vary with lambda? So what we do in this case is to use the WKB approximation of quantum mechanics. So for that, let's understand what WKB approximation means. What does it do? And why it is an approximation? So in quantum mechanics, what we generally do is to solve the Schrödinger equation once we know the Hamiltonian of the system. So if you know the Hamiltonian of a system, you can solve the Schrödinger equation to get the possible energy eigenvalues the system can have. Now it is different from saying that the Hamiltonian of the system itself is the energy of the system. Quantum mechanics just says that if you know the Hamiltonian of a system, you can use it as an operator or a tool to find out the possible energy eigenvalues that the system can have. In WKB approximation, we take a semi-classical approach rather than a purely quantum approach and say that the Hamiltonian itself can be approximated as the energy of the system. And we write E is equal to p squared by 2m plus the potential, which is lambda times mod of x in this particular case. Using this equation, we can find out the p in terms of E and lambda, which is p is equals to root over 2m into E minus lambda times mod of x. Now finally, the WKB approximation says that integral of p dx, which has the dimensions of the angular momentum, should be equal to some constant times h bar. This constant here, we take it to be n plus half. You can take it to be n also, it doesn't matter, because we want the dependence of E with lambda, not n in this particular case. This n plus half just means that we are also taking into account the 0-point energy of any quantum system. Okay, so if you substitute the value of p that I've calculated using the WKB approximation, or the semi-classical approach rather, you can write this equation as integral from minus a to a root over 2m into E minus lambda times mod of x into dx equals to n plus half into h bar. Now to extract the dependence of E with lambda, we use a very general trick called non-dimensionalizing the equation. By non-dimensionalizing the equation, what we essentially do is to take out all those variables or factors which can have some physical dimensions and leave the integrals in the equation in a form so that it can contribute only a constant and no dimension is there in the integral. So for that, what we do is we take out first of all root over 2me outside of the integral, because in the integral the variable is only x, so E is a constant in that case, and then the integral becomes 0 to a 1 minus x by E by lambda into dx. Now what we do is take x is equals to E by lambda times t, where t is some other variable. Now this is the step in which we are non-dimensionalizing the integral. What we're doing is to extract out all the E dependence of the left hand side and the lambda dependence also. so that the integral which will be finally left, which is here in terms of t, as an integral of 1 minus t into dt from 0 to b, will only contribute a constant, and so dimensionally it doesn't matter. So the functional dependence of v with lambda can be written irrespective of what value does this integral give. So we are not bothered about the exact value that this integral will contribute. We're only concerned about the functional dependence of v with lambda, which can be written from this equation itself as e to the power 3 by 2 by lambda is proportional to n plus half into h bar. Here b in the limit of the integration of 1 minus t to dt is equal to lambda into a by e. This you can calculate. It's a simple calculation. It's a substitution in the integrals. And substitution that we've taken as x is equals to e by lambda into t. Therefore, finally, we can write e is proportional to n plus half to the power 2 by 3 into lambda to the power 2 by 3. Okay, this is the dependence of v with n and lambda. Now the question is asking us to calculate the dependence of the ground state energy with lambda. For the ground state, you can just take n to be 0, and therefore E is proportional to lambda to the power 2 by 3. Okay, therefore the correct option for this question has to be option 2. E is proportional to lambda to the power 2 by 3. So thank you for watching the video.